Here we're going to get a volume using cylindrical shells. If you were to use discs on this, you would end up with major complications. If I ended up trying to use discs, they would actually be washers, but trying to find the radius of like this outer washer, I would end up having to do an inverse of the square of the sine function, but I would be outside the principal domain of that inverse function, and I would have to think about adjustments there. So I don't even want to get into it. I want to use the simplest possible method here. And that's going to be shells, because it's pretty easy to write down the height and radius of the shells. So here we go. I'm just going to show like a little width of the shell here, little width of the shell here. We're going to nest a bunch of these in order to build up this solid. So I've got to get all the way from here to here. And down here, the bottom edge would look something like this. Okay, and now I need an expression for the height of the shell, and that's a simple thing to do because the y coordinate connected to this x coordinate here is just sine squared x. So then we go through the usual procedure. I'm going to cut and unroll my shell. And when I do that, it's rather long just because of the way I've drawn this. And I guess I'll put a little bit of thickness in it. Try not to spend too much time just doodling here, but it's nice to have a good picture. All right, my thickness is dx, so I'll just mark that over here. This is the thickness of this slab. The length of this thing is the circumference of what it was when it was rolled up. So it's going to be 2 pi times x. And the height of it is going to be sine squared x. And when I multiply those three, I find out what my dv is. So it's going to be 2 pi x sine squared x dx. Then I use an integral to add up all those volume contributions. So the volume is the sum of all the volume contributions. So that's going to be the integral of 2 pi x sine squared x dx as x goes from 0 to pi. I should make a point here. It might be tempting to try to do this integral all the way from negative pi to pi, but this expression represents the volume of a shell corresponding to an x coordinate along here. So by picking this x, for example, I've covered the volume on the right half of this figure and the left half of this figure. If I picked an x in here, it would cover the volume of a little shell like this. So it's automatically covering that left half. You don't want to accidentally double count and get twice the answer. All right, so what the approach we're asked to use here is to use a computer algebra system to get the exact answer to this integral. This is something you would do with integration by parts, but we're asked to use a CIS in this case. So here we are in Maxima, and I have 2 pi x. This is a good reminder that pi is percent pi in Maxima. So 2 pi x sine of x all squared as x goes from 0 to pi. So that looks good. I hit enter and I get this exact answer. And I went ahead and just used the snipping tool to put that into the slide.